Shown is a plot of potential energy versus distance. Which of the following points are stable and unstable equilibrium? We didn't go over equilibrium, and I didn't read it either.
Okay. It just has to do with these graphs is all.
I think we mentioned it though, right? When both sides of whatever equation of forces are equal.
So that would be equilibrium of forces.
Different here?
Yeah, it's a little different here. Here it just means it's a point where it would stop. So if you go back, it's in chapter 10. These energy diagrams. Okay, energy diagrams right here. So when you draw an energy diagram, it's of the potential energy. So it shows how much potential energy an object has based on where it's at. So like this. So let's see, it talks about equilibrium in here. Okay. So basically, if you think about this graph we have here, this is potential energy. Let's say our total energy is right here. Okay?
How does that happen if it never even touches?
So what are things that can add to your total energy?
Besides the potential energy and the kinetic energy?
Well, that's exactly right. So it's the potential energy and the kinetic energy.
Yeah.
So if you have this much potential energy and this much total energy, what does it mean about this space?
That's kinetic energy.
Yep. So on this graph, if you wanted to find out the maximum kinetic energy, where would it be?
At the bottom?
Yeah. So you only have this much potential energy here, but you have this much kinetic energy. So throughout the graph, all you're doing is transforming kinetic energy to potential energy. And go back to where your fingers are at. That's where it talks about this. Okay? And what if you bring this total energy down? Say, well, what it'll say is it something like an object starts from rest at this point. So maybe this is x equals 1 meter. Let's say an object starts at rest from x equals 1 meter. So if it says it's at rest, how much kinetic energy does it have?
0.
Right. So it's going to be right on this line. Then your total energy for the rest of the time is right there. Okay? So now what's your kinetic energy going to be?
It will have some negative kinetic energy.
Is that possible?
No.
No. So
So kinetic energy just working in the opposite direction, I guess?
Nope. Even then, that doesn't count. So the direction that an object is moving doesn't matter. It's just its speed.
We don't care about thermal energy.
No, we're not worried about that right now. No, not in this class. Okay, so here, this would be the kinetic energy, right? And then here, this would be the kinetic energy. It'd keep going like that. This would be potential, this would be kinetic. What happens when kinetic hits 0 again?
It's at rest.
Yeah, it stops. Will it keep going up and gain more potential energy? No, because there's no energy to turn into potential energy. The only thing it can do is turn back around and go back to the other
So
side.
that means something else is moving it? What does that mean?
Well, if it stops right here, and then you grab it and you push it, what have you done? what your hand has a force and it moved a distance, right?
Yeah, so it's worked on it, I
Yeah.
guess.
So that would mean if you moved it up to here, that would mean you increased the total energy by doing work. But as long as you don't do any work to it, it can only move between these 2 points. Okay? So then what happens if you bring your total energy down to like right here? How far will it be able to move?
Very little.
Yeah, just right here. What happens if you bring it to just to that point right there?
It has no kinetic energy, it can't move by itself.
Yeah, it won't move. So that's an equilibrium position. If you have that much energy in the system, it can't move.
So no
It'll stay
kinetic.
right there. Yep. So this one is called a stable equilibrium position. Okay. So I'm gonna erase this and, well, let's say this line. So where could we put our potential energy, or our total energy, so that all we have is potential energy? There isn't any way to get kinetic energy.
I would have thought that's where it was at.
Yeah, you're right, this one. So if your total energy is right there, the object can't move. But is there any other place on this graph that if you put your total energy there, it can't move?
The bottom too.
Well, at the bottom, but that's not on the actual, that wouldn't be considered an equilibrium position. What about this one? So maybe you put your total energy going right through there. Would it be able to move?
No.
No.
Not at that position, I guess.
Right, even though it could, if you could get it to move over here, it could get some kinetic energy. At this position, it's impossible for it to move there. You'd have to bump your energy up so it could get over this. Right? So these two are called equilibrium positions because they'll stop there. The ball will just sit there and do nothing. And they're also called stable equilibrium positions because you can't get out of them. If you add a little bit of energy, what's going to happen? So let's say you just added this much energy.
Yeah. But then it can move.
Yeah, but where will it move?
Just over that small distance.
Yeah, it'll just move back and forth, right? Okay, so that's called a stable equilibrium position. If you add a little bit of energy, it'll just move back and forth. Same with this one. If you add a little energy, it'll just move back and forth right here. Okay? Now, what happens is it possible to put the total energy right here to get it to stop? Right at that point, you don't have any kinetic energy, it's just potential. Will it stop?
Yes.
Yeah. But what happens if you add just the tiniest amount of energy there?
The potential energy will take over and allow it to move.
Right. So if you add a little bit of energy right here, it's gonna go down this way, or it'll go down this way, and it'll move back and forth across the whole thing. Okay? So these two, the ones at the bottom, are called stable equilibrium positions, because if you add a little energy, they'll just move back and forth. This one is an equilibrium position, but it's called an unstable equilibrium position, because if you add the tiniest little bit of energy, it's gonna go off and it'll fly away somewhere. So that's what it's talking about here in this graph. It shows you the peaks are unstable equilibrium positions, and the valleys are stable equilibrium positions.